talked a lot about how to get this lower bound, on the minimum. But let's assume you want everything in life. So you want the bounds and you want also to get these minimizers for the initial problem. So there is a way to do that with the moment hierarchy, but you need to be lucky. So I introduce this notation about the max half degrees of the polynomials defining the constraints. But in your head, just imagine that every constraint has degree 2. Then you divide 2 by 2, it's 1. Then this number is 1. Just for simplicity. Okay? And assume that you solve your moment program, so the relaxation with the pseudo moments, and you find the moment matrix whose rank stabilizes. So what does it mean? It means that you have your moment matrix with all the monomials up to degree d, and then you take the submatrix with all the monomials up to degree d minus 1. So I say d minus 1 because this 1 is half degree, but it can be more general, it can be 8. So you have the smaller matrix and the big matrix, and they have the same rank. Then you are a full winner because you solved the initial problem in the sense that the bound that you obtain as this finite relaxation order is really the minimum of your polynomial. And also, all the information you need is encoded in this moment matrix, and in particular, the coordinates of the minimizers of your problem. So you get the minimum and also the minimizers. And once you know that the rank stabilizes, then you can run a linear algebra procedure to recover the minimizers. And for the infinite dimensional problem over measures, the one that you solved at the beginning of the course, it means that you can actually extract this Dirac measure. So you will get a weighted sum of such Dirac measures, and every Dirac measure will be supported at the different minimizers. So if you get a rank of 4, it means that you can get these 4 minimizers. And you can use available software to do that. For instance, Globsipoli in MATLAB or Tezos in Julia. And it's quite easy to implement. It's like, I don't know, 20 lines of code maybe. We're implementing the moment hierarchy, so this is the tutorial project I give. It will be a bit longer, but this is very straightforward once you know the linear algebra procedure. And we can also do that in the sparse case. In the correlative sparse case, so here I have, so it's more complicated. This AK here depends on the constraints seeing the first subsystem, the constraints seeing the second subsystem. But for simplicity, assume that all of these guys are 1. We have degree 2 constraints, and everybody has half degree mass. Then you can do the same reasoning, but you need to check it for every pseudo-moment matrix indexed. So seeing the first subsystem, seeing the second subsystem, and so on. So you need to check that the rank stabilized on every subsystem. That's the first thing to do. And you also need this very strong assumption that if you take the common part of 2 subsystems, then the rank of the resulting moment matrix has to be 1. So why is that? Because if you run the extraction algorithm on every subsystem, then you will get some minimizers that are maybe not minimizers of your problem, where you have access only to the coordinates of each subsystem. So you will have access to x1, x2 on one side, and x2, x3 on the other side. But the x2 coordinate might not be the same, right? So then you will have to organize some, matching to check whether there is consistency between these minimizer coordinates. And this rank 1 condition ensures that basically the x2 coordinate will be fixed. I'm not going to enter into much details. So the second assumption is not mandatory, strictly speaking. And there are papers, so for instance, by me, where they do not assume that. But in the paper by Jean Bernard, where he proves that, he does this very strong assumption. And also, so if you want to try your luck, you don't need to assume anything about the graph. So you don't need the graph to be colored, you don't need the running intersection property to hold, because this thing is so strong, much stronger than assuming that the graph is colored. So you take whatever subsystems you want, you try to solve the associated sparse relaxation, and if you get these two conditions, then you are a full winner at a very cheap price. Okay. So yeah, this is what I wrote. Running intersection property is not required. Exclamation point. Any questions on this extraction business? Yes.
Then if you would run the sparse hierarchy without having the causality, you would just get results that don't tell you anything, so they don't have to be proper bounds to your problem. Or
so in any case, you will always find lower bounds on your problem, but you won't have these convergence guarantees. Basically, one way to see that is that in the dense case, you have one staircase of bounds reaching the minimum of F asymptotically. So also you have one staircase in the sparse case. But if the running intersection property doesn't hold, this staircase might lead you to something strictly less than the minimum. So there are available counterexamples in the literature where you really get something less than the minimum. So actually there is one in the exercise session. Any other question on that? Okay. So I'm a bit late, so I will skip a lot of things on correlative sparsity, but you have access to them in the slides, and I will go to term sparsity. Okay, so the Newton polyp. So no, but that's a very important object also in other fields, right? So I would say that the first example of term sparsity is due to Reznik in '78. So when I think even at the time when he wrote his PhD thesis. So he got this very nice idea. So here you have a polynomial in two variables of degree 10. So if you run the dense hierarchy, it will be quite expensive. And then, so the idea Reznik had is you build the support of your polynomial. So here there are 4 terms. So there are 4 points in the support, right? The 4 orange dots. And then you take the convex hull of that. And then you shrink it by 2. So you have this big triangle, the convex hull of the support, and then the small triangle, the shrinked one. And then you take all the integer points, the integer lattice points. And what Reznik showed is that if the polynomial has a sum of squares decomposition, then every SOS should be supported on this set of points. So it's quite powerful, and so it means in particular for this example that well, if F has a sum of squares decomposition, then it should be written as a vector matrix vector product, where the vector are basically the monomials supported here. There are 5 points here, so there are 5 elements in this vector corresponding to these monomials. Is it clear this for everyone? And so if F has an SOS decomposition, then it means that Q, so that there exists a Q, maybe a lot of Q, that have non-negative eigenvalues. Okay. And here comes, I think, the best exercise of this course. So this is the Motzkin polynomial. So who doesn't know the Motzkin polynomial? So the Motzkin polynomial is, I think, the first counterexample of a 2D polynomial that is non-negative, so on R2, but that is not a sum of squares, and we will prove that now. by using the Newton polytop. So first you need to compute, to represent the Newton polytop of F, shrink it by 2, check what would be the support of the squares if Motzkin would have sum of squares decomposition, and then arrive at a contradiction. So please take 2 or 3 minutes to do that. So I will show some beautiful drawings. Find results.
I'm Right. Yeah, I was happy to be ready.
Get it though.
You're awesome. Good.
That's not good. I believe this.
Can you repeat what's the what implication we need for the not SOS?
It's a proof by contradiction. So you need, so you assume that F is sum of squares. And then by Resnick, each square will be supported in the shrinked Newton polytop. Then by checking which terms should appear, you should arrive at a contradiction.
Here's going to be trivial to it except for this curve root. Because it's a negative one, but then it will
Have it?
this one. Next
Okay. So we check the news. 2, 3, 4. Of course, the original Newton polytope has it's a convex hull of 4 points. The origin 2, 2, 2, 4, and 4, 2. So now if I scale it down, I get this. And of course, these 4 points are already all the lattice points that we have. So everything, the base of each square would need to be supported in these 4 things. And now, if we square any such expression, observe that the term x1 squared, x2 squared, it only appears as the square of this term. It doesn't appear as any mixed term. So it will always come with a non-negative coefficient. But we're supposed to get something negative, and that's a contradiction.
Perfect. Is it clear for everyone?
Essentially, this point cannot be expressed as a how is it? I cannot express it as a midpoint of any 2 of the other points. So it cannot come as this x1 exactly can come as the next term.
So this also always, if it's like let's say a proper dilation, if I scale it by some integer, and I find that my lattice points are always like the previous lattice points are also the one of the dilated polytope, then this is always true.
Well, it depends. It depends what is your objective polynomial, right? If you would have a plus here,
And then it's
then it's a sum of squares. So it depends on the coefficients. And it's funny because if you look at the historical proof, then they do a reasoning. I forgot who did that. They do some kind of reasoning like that, but without exploiting term sparsity. Then it's a huge proof. Like here, you just nail it in 1 minute. He did it. Okay. Well, many thanks. All right. And so basically, the term sparsity methods that we designed are variants of this. And generalization also to the case where you have constraints. Because very often you have constraints in your application. So again, let's take a complicated polynomial with quite a lot of terms. So here it's a 3D example. And let's do it first in the unconstrained case. So if you apply the Newton polytope method, then you get 1, 2, 3, 4, 5, 6 monomials. And does it work? Does it work now? No, is it okay? Yeah, I can't hear it myself. So then you have this vector matrix vector product. So the Gram matrix here, Q has size 6, and inside there are 6 times 7 divided by 2 unknown entries. Okay. But then what you can do is that, a bit similarly to correlative sparsity, you create a graph, and the nodes of this graph are these monomials. So they are not variables anymore, they are terms, they are monomials. So you have 6 terms that are represented here. And then you draw an edge between 2 nodes if the product appears in F. So for instance, here, there is no edge between 1 and x2 because x2 doesn't appear here as a term. But there is an edge between, I don't know, x1, x2, and x1 because the product x1 squared x2 is here. Okay, you do that. So exploiting the Newton polytope is basically considering this graph but completely connected with edges everywhere. So what we did was just removing some of the edges. And then as for correlative sparsity, why not? You take your favorite Cordell extension, so either the very, very brutal one, where you just complete every connected component has a complete graph, or an approximately minimal causal extension. And then you replace this matrix Q, this graph matrix Q, by a sparse matrix indexed by this graph. So either the very first graph or its causal extension. So that's the basic idea of scarce sparsity. That's it. And if you do that, then you have less entries to consider because there are prescribed zeros in your 15 instead of 21. Is it clear for everyone, this construction?
So would it make sense to add a vertex maybe called x2 square here? Would it help? Because you already have x2, but maybe using different powers of the same variable may get to sparser graphs.
So at the beginning, you pick a basis. So if you pick a basis where x squared is, then you should put x squared as a node.
But there are plenty of bases.
There are plenty of bases.
Some lead to sparser graphs than others.
Exactly. So here we pick the Newton polytope basis, but you could pick your favorite one. And in practice, what we do is that we take the canonical basis.
So it's not assured to be the most optimal.
It's not?
It's not assured to be the most optimal way.
Yeah.
It's not a constructive way.
Yeah. Also, I will talk a bit about symmetry adapted basis. So if you have a symmetric problem, in addition to be sparse, then you should basically take as nodes the polynomials of your symmetry adapted basis. Okay. And so in the constraint case, so basically you pick the step of the hierarchy, and you pick as a basis the set of all monomials of degree up to d. So this is your set of nodes. Then you add an edge if the product appears in your input data, or if the product is a square. So since you are looking for sum of squares with composition, you should really make sure that you will have squares. And actually, so this graph will basically determine some block diagonalization of your moment matrix and also your graph matrix. So this is a more complicated example where you have an objective function and some constraints. So in life, you get more complicated Bern's sparsity by Bern's graph. And so basically what I showed you is just one step of a general procedure where you can add more and more edges. Okay. So the way you will have more and more edges is as follows. So as I said, this graph will index your moment matrix. So every moment variable that you have will correspond to an edge. So first, you need to make sure that everything is consistent, that the resulting moment matrix has pseudo-moment variables appearing where they should appear. And this basically is ensured by the fact that if you if you have an edge here, it means that the product x1, x2, x3 should have an associated pseudo-moment variable. So if in another component of your graph you have x2, x3, and x1, then they have to be connected as well. Okay, so at the beginning, when you build the very first graph, this you don't see. But when you do this causal extension step, then you need to make sure that all the support extension is satisfied. So here, for instance, there is an edge between, you have to add an edge between x2 and x3 because there is one between 1 and x2, x3. So the product x2, x3 has to be there. Okay, so that's how we will get more and more edges. So we will have a hierarchy of graphs leading to a hierarchy of moment SOS programs. So it's a hierarchy within the hierarchy. It's a two-level hierarchy. Okay, so when you read the papers, there are a lot of indices, but that's life. I mean, you need one additional index to take into account the fact that there is this additional hierarchy. Okay. So yes, the two-step procedure is as follows. So you need to do this support extension. So make sure that every pseudo moment variable will appear consistently, and caudal extension. And then you have a lot of choices about the caudal extension that will lead to several hierarchies. And by iteratively performing these two steps, you have this two-level hierarchy of bounds. So do you have at least an intuition of how it works? And then, so what happens in practice is that you build your graphs, and then you take the clicks of this graph, and you index every moment matrix by this click. So you will basically block diagonalize your moment matrix. I will show you right after some examples. So in the moment relaxation, you replace the dense matrix with this submatrix. And you do the same for localizing matrix. I won't give you too many details on that. And doing so, you obtain the term sparsity, exploiting moment hierarchy. So every dense object is replaced by this block diagonal object. So for those who know symmetry exploitation, this is extremely similar. And for actually a good reason, it's because this thing is actually mimicking what happens for very specific symmetries. I will talk about it in a minute. So as I said, there are different choices of caudal extensions. So this is an approximately minimal extension, and this is the maximal caudal extension. So basically, you complete every component, you make it into a complete surface. Okay, and then there are some nice convergence guarantees, and also some nice bounds. So if you fix a sparse order, so the sparse order is the number of times you added new edges. So if you fix a sparse order, but then consider two levels of the initial hierarchy, you get increasing bounds. It's not too hard to prove. And also at every relaxation order, if you increase the sparse order, then since you get more edges, then you get better bounds. But the nice thing is that infinitely many steps, the bounds that you obtain converge to the dense relaxation. So you are not conservative anymore. And I mean, the proof is kind of trivial, right? I mean, if you add edges like a brute, then at some point you will have the complete graph, and then you will just solve the dense problem. Yes.
But couldn't you still get independent?
Yes, exactly. Yes, because, and this I will talk later, because this thing is mimicking the sign symmetry exploitation. Okay, and so actually this construction, so we didn't realize it when we first designed the algorithm, but this algorithm is mimicking what happens when we exploit sign symmetries. If you use the monomial basis, not the Newton polytope or your favorite basis, and also if you use the maximal caudal extension. So let's see how it works on examples. So let's take a problem that is invariant under certain sign symmetries. So here this polynomial is invariant when you flip the sign of x2, not the size of x1. So you can select a monomial basis. So on purpose, I reordered monomials so that here, in this first part, you have the invariant polynomials under this sign flip. And here you have the equivariant monomials, the ones that are not invariant. Okay, so I mean, x1 and x1 squared do not change when you flip the sign of x2. They don't even depend on x2. And x2 squared also remains constant. While these two monomials have sign flipped. Okay? And so if you apply term sparsity, okay, then you will have two components. So the first with the 4 nodes and the second with these 2 nodes. So here, there is an edge between x1 and x2 squares because x1, x2 squares is here. but there is no edge between 1 and x1 because, well, x1 is not there, and also x1 squared, x2 squared. Oh, no, but there is a mistake. But there should be an edge here.
Right. No, the edge between x1 squared and 1 shouldn't be there. Because x1 squared is not.
Yes, because we need to have squares. Okay, this is, so I changed it yesterday because it was wrong and it's still wrong. There is an edge, so there is an edge here. Because squares should be always there. And there is an edge here because, yeah, it's the same. So x1, x2 squares is there. But it doesn't matter. After Cordell extension, everyone will be there. Okay, so the maximal one, after the maximal one, so here I have one connected component that is complete, and also here. And this, so this is really the block diagonalization that you do when you apply sign symmetries. So why is that? Because this basis here is the basis adapted to sign symmetries. And in general, one can show that the graph that you obtain always corresponds to the block diagonalization of the maximal sign symmetry group. Yes.
Why should there be an edge between x1 squared and x2 squared?
Because you need to ensure that all the squares are there. So you are looking at one sums of squares decomposition. So basically, when you have your moment matrix, all the diagonal elements should be there. Because if you fix one diagonal element to be 0, then after reorring, it means that you have some bands of zeros appearing. So that's too restrictive. I mean, it can work, of course, for some problems, but in general, you should be sure that all the squares are. Okay, and this is another example, also invariant under the same sign flip. And now, instead of taking the canonical basis, let's assume that we take the Newton polygon. And so in this case, block diagonalization that you obtain that corresponds to sign symmetries is this one. So here you have the 3 invariant monomials, and here you have the equivariants. So this is what you obtain if you apply sign symmetries. But now let's apply term sparsity. So if you apply term sparsity, so actually there is no edge between x1, x2 and x1 square x2 because x1 cube x2 square is not there. So at the end, the term sparsity algorithm will converge to that. So it will converge to a different thing than sign symmetries. So if you want the same as sign symmetries, you should use the canonical basis. And actually, so in some cases, the term sparsity is more economical than the sign symmetry. But maybe the bound will not be good. Is it clear somehow?
But in sign symmetries, why does the edge exist on the small subgraph?
Well, because in your symmetry adapted basis, you will have these 2 blocks. Block of invariance, the block of equivariance. Then you just
So you build that
consider these blocks
from the, so you first build the blocks and then you build the graph according to the block.
Exactly.
So you just said that, so is this whole procedure dependent on the basis?
Yes. Because if you pick a different basis, then of course the edges will be different because you don't consider the same set of possible products. So here we are at a very heuristic level, right? So you can pick whatever basis you want. Maybe it doesn't make any sense with respect to the initial problem. And if you start building this sequence of graphs, then maybe it will be completely different as the one that corresponds to the dense or the symmetry adapted case. If you want strong convergence guarantees to the dense bounds, then you need to pick the canonical basis.
Yeah, but with respect to your original motivation, which is to decouple variables that talk to each other, or you mentioned these electrical networks, for example, this should not be basis dependent, right? Two variables are correlated. This is independent of the basis you use to represent the polynomial.
Sure, but there are different ways of doing this basis change, right?
Mm.
And so it's a bit. So there are some basis change that will give you convergence to the actual minima, and some basis that would not give you convergence guarantees, but maybe they are good enough so that you get a reasonable bound.
If I remember correctly, this correlative sparsity where
It's the same for correlative sparsity.
but you start from a polynomial and then you construct the Hessian. Then you look at the Hessian as a matrix and you look at where you have zeros or not. When you have zero, it's not correlated. Two variables are not correlated.
Yes, exactly. Yeah, the product.
And so it's independent of the basis. It's because you list the variable, but you don't use a basis to represent the polynomial to differentiate it. Right?
Oh, yeah, but you could imagine that you do a change of basis. So for instance, you define a new variable that is x1 plus x2, and you rewrite everything in terms of these new variables, and then you do the same. Then maybe the zeros will not be at the same place. For instance, if you use symmetry adapted basis. Then... Yes. You had another question? Yes. Okay. So that's the key message of term sparsity part. So TSAS preserves the block structure related to sign symmetry. So we are not smart enough to see that when we first designed the algorithm. So we are just really mimicking what happens when you exploit sign symmetries. And also we were not smart enough to realize what happens in general for general symmetries. So I will mention that a bit later. So there are some convergence guarantees. You just exploit term sparsity. And then you can do the combo, right? Why not? So what about combining all these different sparsities? So the combo works nicely. So the best thing is first to apply correlative sparsity. Then you have your different subsystems. And then you apply term sparsity to each subsystem. It seems just very easy to state this and to write it on the slide with just 2 lines, but it requires a bit of care. You need to really take care of the different subsystems also when you do these different extensions. And so we have implemented all these algorithms in the library. And for some huge problems, if you have a lot of sparsity, then you can get decent results. Of course, it doesn't work for all problems. And so the toolbox allows you to pick the kernel extension. So sometimes the problems are so big that the maximal one doesn't work. So then you should prefer a more economical one, even if the bound is not so good at yet.
Can you do the opposite though? Start with term and then do correlative something? Or it's way worse because in term.
I'm not sure how to do that, but I think it might be equivalent.
Then you would interconnect the graphs, right?
Shouldn't be no equivalent.
Yeah, you should be able to compute subsystems for every graph that you obtain. I think it's doable. I think it's going to be equivalent. I haven't tried to do that. But let's see a bit of graphs to give you a taste of how things go when you apply either one or the other or both. So here, for instance, I apply just correlative sparsity. I have a 6-dimensional problem. So this is the resulting graph, and then I can compute the cliques and the subsystems. And then I can apply term sparsity for every subsystem. So this is the graph that you obtain when you do that. Okay, so it's quite sparse graph. So for the first click, for the second click, and yes, okay. So this is the graph that I applied. Now, if I only use term sparsity, this is the graph I obtain. So it's worse than the thing I showed before. I mean, I don't know if you trust me, but it's worse. There are much more edges. Yes. Because in particular here everything is connected. Everything is connected between the squares, and I have this 6-dimensional problem. While I only get like a full connection between the subsystem with 4 variables and the subsystem with 3 variables. Wow. Okay. And then, so what we recently noticed also is that actually you can build a term sparsity algorithm for every symmetry adapted basis. So the initial one we designed was actually for style symmetries, because we were just thinking about monomials, that it's easier to implement. But actually you can do a similar construction for every problem that is invariant under a discrete group. So that's the basic idea. So I have a finite group. My polynomial optimization problem is invariant under this group. And then I have the set of G invariant polynomials. And then, so people who do symmetries, they like these averaging operators. So here we are summing over all the group elements, and Fe means that in F, you do the changes corresponding to this group action. For sign symmetries, you replace x2 by minus x2. For permutation, you replace x1 by x2 and so on. And so the algorithm is pretty much the same. So you compute a symmetry adapted basis. This is your set of nodes. But now every node corresponds to a polynomial, not necessarily a monomial. And then you connect 2 nodes if somehow the product support intersects the one of your polynomial. So it's a bit more complicated than in the case of sign symmetries. And or also the averaging of all the squares. So you have several terms when you do this averaging, because you obtain polynomials at the end, not necessarily monomials. And also when you do product between nodes, you have polynomials. So you need to check that these 2 polynomials have some common support. As soon as you have some common support, then you need to connect the edges. And then it's exactly the same as for the usual term sparsity algorithm. So you compute the kernel extension and you start again until it converges. So let me show you an example. So here it's a problem that is invariant under all possible permutations in 3 variables. So I have my invariant basis polynomials. So it's the sum of powers of all the x. And here I have also this basis element. And then I have the equivariance polynomials. So these guys are not invariant. And then I build the symmetry adapted basis. So I have the invariance here and the equivariance. And the initial graph I obtain is this. So first, there is no connection between B1 and this small 2-node graph. And there are quite a lot of connections between the invariance basis elements. So after kernel extension, then yeah, I get the complete graph here. And after the support extension, I have a connection that appears between B1 and B2. So building this graph is one of the exercises of the tutorial session. Understanding why we obtain that. Any questions on that? Yes.
Why is it important that the group is finite?
Oh, I don't know. I think all this theory works also for general groups, because you take a truncation, so that could work. I think Cordian should be there to reply to this question. I'm not the most here. Yes.
No, I was thinking about if you take Lie groups, for example,
Yes.
then you just can just take the generators of the Lie algebra, and then it should work, right?
Yeah, it's not finitely generated.
The problem is, yes, so you will have an infinite basis,
Yeah.
but then if you decide to truncate it, yeah, why not?
Then you approximate.
So who is working with symmetry exploitation here? I forgot. No.
Not in the room, at least.
Oh, look at What do you think about this question, Lou?
I think for compact continuous groups, right, you always have, so you consider your polynomial ring as a representation. And then when you truncate, it's a finite dimensional representation. So all the irreducibles that you find inside, you can do the same thing with those. So you get the same symmetry exploitation mechanism basically, but I'm not sure about how this works with this term sparsity setting. I will look into this at some point.
Yeah, I think if it works for the symmetry exploitation, it should work for term sparsity, but then you still have this Schur's lemma that you can apply, right? So this block structure. Thanks. Any other questions on that? Okay, so that's, yeah, as I said, that's one of the exercises to get this graph. So yeah, so the other key message is that there is a term sparsity algorithm for your favorite discrete group. Yeah, so if you want to know more, you can. So there is this recording of the Poema lecture that Cordian gave at the time, where he explains how you build this different block diagonalization. So he starts with matrices, a bit like I did. He starts with matrices and then goes to polynomial. Okay, and so now I will give you an example of just to illustrate the kind of speed up that you can obtain by exploiting all these kind of sparsities. So one problem we worked on is the one of alternative current optimal power flow. So this is a problem that interests the transmission operators. So either in France or in Europe, also in the US, they have different needs and also different requirements for how good you should solve, how well you should solve their optimization problems. So the basic problem is to minimize the operator cost, so the active power injections that you have in your network. And of course, you have these physical and operational constraints. So we'll talk about that a bit later. But the thing is that there is this benchmark, there is this library where you can access to these different instances. And so this is an artificial version of the initial problem. And when I asked if this was realistic, they said, no, it's not so realistic, but if you don't know how to solve these artificial problems, then there is no hope that you will be able to solve the real one. So this is some kind of simplified version of the problem. And it's still quite open, so we still don't know how to solve that efficiently. And so just to give you a flavor of why the problem is hard and what do the constraints look like. So the network is a graph. So at every graph you have this bus. And then you have some from and two edges, depending on the current. And in some of the buses, you have generators, so electricity generators. And you have a power demand, so depending on the consumers. And so the variables of your optimization problem are the voltages and the power generation. So you want to know how much you should use this generator or this one, or maybe shut down this one. And so the physical laws that are used are the Kirchhoff law, so the conservation of currents. So you have this additivity of currents at every node. And the Ohm law. So personally in school, I didn't learn it like that. It was voltage equal to the resistance times the current. So I don't know why they do this thing with the inverse of the resistance. And then you combine everything. So basically the power is the product of the voltage and the current. And then you have this nonlinearities that appear, right? So this is just the conservation of energy that is written at the bottom. And so yeah, these equations make the problem very hard to solve because it becomes quadratic, basically. So it leads to this, what they call the power flow equations. But okay, so yes.
Process this for a moment. So this S is the power demand, but so the bus has generators, right?
Some buses have, not all.
What is a bus?
Many people that looks like some kind of connection that you have. I don't know, like if you think about the electrical plugs that are here. So there will add new nodes in your whole electrical network. Right? But you might not have like a power plant here in the University of Tromsø. That's it.
Okay, so then if the city has a generator and also supply and demand.
Exactly. There are very few generators compared to the number of them.
Are they vertices or not? The graph.
So the vertices are the buses. And in some of the vertices, you have generators. Sometimes several, sometimes zero. For instance, I don't know in the University of Tromsø how many generators they do. Maybe zero. Okay. So the optimization problem looks like that. It is a very hard optimization problem for two reasons. The first reason is that there are thousands of variables. That's ugly. Second reason is that every variable is complex because, current. And these quadratic constraints are also very high. That's what makes the problem complicated. The objective function they use in this artificial version is either degree 2 or degree 4. They like to have it degree 2 because then you can apply this first order relaxation. And then, so basically you have this also this bound constraint. So basically every voltage should not be, the modulus of every voltage should not be too high, otherwise everything will explode. And that's it. But there is a lot of structure in the electrical network graph that you can exploit. And so in particular, you can exploit correlative sparsity and down sparsity. So here on the left, only correlative sparsity is exploited. And on the right, we do the combo. So we exploit both correlative and down sparsity. So let me tell you a little bit about the different data. So N is the number of variables, so the number of nodes. And M is the number of constraints, so the number of optimal power flow constraints and also the bounds that the operators prescribe in order that the system doesn't explode, for instance. So you can see that this is completely unreasonable. That's crazy. So we have thousands of variables, tens of thousands of constraints. But correlative sparsity is not that bad because it leads to SDP blocks with size 200 or 500 for the first two problems, and basically around 1,000 for the last problem. But it only works when the size is not higher than 200. So the interior point solver that you use doesn't want your blocks to be too large. And in this case, we can estimate the gap of the optimization problem to be less than 1%. So I think in France, they are quite happy if you get a gap less than 1%. I think in the US, they are not happy. I think in the US, they want less than 0.1%. I never understood why. So solving this problem takes 1 hour on standard laptop. But for the second problem, the third problem, the fourth problem, your interior point solver tells you run out of memory and tells you to get stuff. So this is not possible to solve the problem. So I don't know if it's clear for everyone what the gap is. The gap. So you have your minimum, right? And you want to take the minimum in sandwich. So you first compute this lower bound by the moment SOS hierarchy or whatever technique you prefer. And you can also compute an upper bound by using any local power. And then you basically, this gives you the gap. So how close these two upper and lower bounds are. So here having 1% means that they are not too far from each other. And now if you do the combo, then the block size becomes ridiculously small. Now it's 40, for instance. And so here you get a gap that is slightly worse because you introduce a bit of conservativity. But still, you can get really good gaps for this huge problems. So that basically means that even if the problem has a lot of variables and constraints, actually there are really like subsystems that make sense, and we were able to find these subsystems. And of course, I didn't display all the examples where these techniques do not work, but there are a lot of instances where the gap is more than 20%. So there is still a lot of work to do. Yeah.
So if you can calculate the gap, then the objective of using the moment SOS techniques is just the certificate of the.
Well, but there is somehow always you can run any local algorithm that will reasonably converge to a local minimum.
It's the opposite. You have an idea of how good is the local minimizer, provided you can compute the bound. Otherwise, you don't know how far you are.
Yeah, exactly. So it's just to know that you're doing good with the local, like how good you're doing
Yes.
with the local.
Yeah, absolutely.
Yeah, I mean, yeah, you're right. So if you have a good gap, then it means that both methods work well. But maybe your
have a good
maybe your lower bound is very good, but the upper bound algorithm is doing nonsense. And then you think that your lower bound is not so good, but actually it's the upper bound.
But also this gap is like you don't know conversions, right? So the gap could be like maybe the actual attainable point is the local solver, like the local solver gives you the exact point, but the gap is 20%.
Exactly.
But that doesn't mean that local solver is bad, right?
Exactly. Yeah, but this is actually what happens most often, right? The local solver is extremely good.
So this only works if the gap is small. Like the information you gain is only if the gap is small.
Both techniques make the sandwich very thin.
So in this example, the correlation sparsity has a very nice physical interpretation, right? Because the reduction is not that strong because there's still a high connectivity in the network, but how can we understand the term sparsity? It's nothing we can.
Well, this is no. I mean, the meaning of the term sparsity here is which products appear in your optimal power flow constraints.
Because there's like in network theory, you also have like a neighbor. Okay, there's a certain word for it, but you have correlation of a neighborhood, and then you have the sort of mean correlation of nodes in your network, and these are two different sorts of connections. And so the correlation sparsity is definitely how connected is one point to another. But then there's also a different measure of connectedness, which is what is the size of a neighborhood, for example.
Yes, but I don't know if it applies there because so here the degree 4, for instance, the degree 4 monomials will only appear at the second level of the hierarchy, and they never appear in your initial problem. So the monomials that you get at the second level, they are not even in the input problem. They come from this higher degree sums of square certificates. I don't know if there is a clear interpretation of it. That's an interesting question. Any other question? Yeah.
So you said the problem is very big, so this is like a toy instance of it, or like a smaller version, like this N and M that you have as the numbers?
So actually, this last one is almost a problem that RTE solves on the French network on a daily basis. It's still an artificial version, meaning that there were a lot of simplifications on the objective function and so on. How much time do I have left?
30 minutes.
30 minutes?
Yes.
Because I see 5 and we started. Oh no, we started back at 4. Okay, I thought I was already out of time. Okay, that's good. We still have, okay, and now is the time to market the work of other people, including people in the room. There are more and more applications of these sparsity techniques, and also new methods, and especially so there. Yes.
So in this examples you were showing, so the local solver depends a lot on the starting point.
Exactly.
And so here they are chosen, there are many tests or what.
So here what we
special
do,
choice of.
so here what we do is that we take the moment matrix that we obtain, the pseudo moment matrix. We take the first coordinates, so the first entries, and we feed the local solver with that. Usually it gives, it's completely heuristic, but usually it gives reasonable answers. So so basically if you almost converged, if you are really close to the coordinates of a global minimizer, then that will help a lot the local solver because he will basically slip and find the global minimizer. But if you are very far, then it's going to be nonsense.
Is it known that this local minimizer is the global minimum in these problems?
So there can be a lot of local minimizers that are not global in this problem.
Yeah, but the one you choose, you find. Yeah.
The one we choose is really given by the relaxation. So it's maybe not a very good approximation of the global minimizer.
So
What do you mean? Do you mean can you extract the solution with the rank stabilization procedure?
no, so you say you take the first moment,
Yes.
use this as a starting point.
Yes.
And compute the local minimizer.
Exactly.
So is this local minimum the global optimum of the problem?
Oh no, not always. I mean, for all of these problems, it's not right because otherwise the gap would be 0.
It could be, no? Even if the.
Oh no, it could be.
No.
No, we don't know.
Yes,
We don't.
it's not.
It's not.
Well, if the gap was 0, no?
If the gap was 0, then you would know, but then you don't.
How does this compare to like other theoretical ways of picking the first point?
I think I will not state it as a theorem, but I think if you do random initialization, then it's pretty bad because there are thousands of variables. There are a lot of ways to start. And what we observed is that in average, it was giving better results to do that, but it doesn't mean it is.
Oh, then it's not only about certificate. You're actually using it for improving the solvers, right? So it's
Kind of, yes.
that's good.
But I don't claim it's the best choice. Okay, so marketing. So this correlative sparsity techniques that were used to solve a lot of problems coming from robotics and robust geometric perception. So that there was the thesis of Han Yang during COVID. And so now I found a job in Harvard. And he has this group doing robotics, and they do amazing things. They do a lot of, they know how to market it. It's quite interesting. So you can check the website of this Han Yang and the group. So there were recently a lot of activity on polynomial matrix inequalities. So far I only mentioned scalar polynomial problems, but so part of the theory also works when you, for instance, you want to minimize the eigenvalue of a matrix with polynomial entries. There have been some work for unbounded optimization. It's more on the theoretical side. So during COVID, there were 2 theses on the topic of dynamical systems and set approximation, where it's basically much harder to apply the correlative sparsity techniques. So there was the thesis of Matteo Tacchi, the thesis of Corby Schlosser that you might have met. So this is still quite open. So the intuition behind that is that if I give you a dynamical system with very sparse input data, the set of initial conditions described by very sparse polynomials, the general state constraints also described by sparse polynomials, well, it doesn't mean that the set of trajectories will be sparse. So these people, they worked very hard to find the nice assumptions that guarantee that you will have sparse description of the trajectories, basically. Then there was also studies in the group about these neural networks. And so during Poema, we also designed a new kind of sparsity with Monique Laurent and Andris, who was also a Poema student, which is called ideal sparsity, where you assume that you have some of the products between variables that is equal to 0. Then you can consider lower dimensional systems. And then recently, Juan Tenos students derived a new type of sparsity called Lorentz sparsity. So if I understood correctly, it's somehow connected to correlative sparsity. But it's for tensors with Lorentz. So please ask Lorentz about. Okay, and so in the remaining 10 or 15 minutes, I will talk about nonlinear moment problems. So extension of the hierarchies, nonlinear moment problem. So we saw that 2 hours ago, covariance problem. Do you remember it?
It was with R4.
Exactly. It was with R4, but the interesting problem we tackled.
You cannot remember.
I didn't
remember it.
Okay. So you're right, Didier. And also there were only 4 terms, and now there are a lot of terms. So people who know quantum information will recognize the analog of I3322 here. Yeah, this is what it is. And so yeah, so we are interested in the maximal value of this quantity, also in the quantum case, but Tony will talk about it tomorrow, I guess. And so our physicist colleagues, we didn't invent this problem. So our physicist colleagues invented this problem. And they didn't know how to compute the maximum. So what they did is that they picked a lot of measures and they tried to see what was the value. So they did as the local solver does. But this is already not easy. I don't say it was not easy. So, and if you do that, then you get a lower bound of your maximum to be 4.5. So then the question is, what is the actual maximum or not? So at the end of the talk, I will answer this question. I will read the answer. Yeah.
So when you say that they took a lot of measures, does that mean that they sample?
Yes, they sample.
They take a grid of R6 of this, and then they optimize the weights. Or?
So here the constraints are very simple.
Okay.
Then you can.
Yeah. Oh yeah.
And you can pick some.
There are finitely many points. Okay.
And there is another problem coming from also quantum information. Okay, so here the objective function is nonlinear. Then we also found that quantum physicists were interested in the problem where the objective function is linear, so it's just an expectation. But the hard problem comes from the constraints. So I will show you in a minute. So I don't understand the meaning of this. I still don't understand why they picked that, but it is what it is. So apparently it was interesting because it could lead to higher violations, but I don't really understand the geometry of the problem. So, yeah. If someone understands, please. I asked all of them, but I couldn't get a clear answer. What is maybe easier to understand is the bilocality constraint. So basically it tells you that you have three sets of observables. So you have Alice, Charlie, and Bob in the middle. And basically, every time you have a product of Alice and Charlie operators, then you can factorize, with one term being the product of Alice and one term being the product of Charlie. So here I wrote the highest degree one, but it works for any product. So if you have A1, C1, then you will get the product of A1 times C1. So this is what I mean by similar factorization control. And so same thing. So our dear physicist colleagues picked some mu and tried, and they could find a lower bound of 3 for the maximum. And they conjectured in this paper that the maximum was 3. So I will tell you at the end what the actual maximum is. And yeah, so this is a rough explanation of the problem. So it's about entanglement swapping. So at the beginning, Alice and Bob are not entangled. They are entangled, also Bob and Charlie. Alice and Charlie are not directly entangled, but after this observation, then they might become entangled. But again, so I think Tony might talk about that. Just for self-containment of the stat. Okay, so how do we deal with these nonlinear problems where, well, we introduce a new class of polynomials? These polynomials are called moment polynomials. So the variables are the usual variables that we use for classical polynomials, x1 to xn, but the coefficients are more complicated. So the coefficients, they are so-called combination of formal moments. So a formal moment is just a variable that you introduce. And the important thing is that this variable, this formal variable, you will evaluate it at a measure. So you pick your favorite measure, and then this formal moment variable evaluates to this quantity. So this is a real number. This is a real number, and this is a variable. Okay? Is it clear? And then if you take sums of moment products, then you obtain what we call the pure moment polynomials. So they are just products of integrals, sums of products of integrals when you evaluate them in a favorite measure. Okay, so this is an example of a pure moment polynomial of degree 4. Okay. And this is an example of a general moment polynomial of degree 6 or 8, sorry. Okay. So what's very confusing maybe when you see that you think there is a connection between this variable, between this x1 and this x1. So yes and no. So here you are integrating the product x1, x2 to the 3 over the support of your measure. So I don't know, maybe the support of your measure is the ball or the unit cube. And here, this is basically the variable x1 that at some point you might want to evaluate also on the same measure support. So basically, these variables are connected via the measure support. But I will tell a bit more after. Okay, so if you take your favorite measure on R2 with first order moments, then maybe you take your favorite point, which is 2, 3, and then you evaluate this polynomial. Well, you obtain 2 times 3, so here, times the integral of x1, x2 to the 3. So there is no connection anymore between these 2 and this x1, right? So here you are integrating over the support of mu, when you only take x1 equal to 2 when you multiply.
This variable y.
Exactly.
As
Would it be +2 or +3? Before the -2.
Oh, you're right. There is a typo. It's 3. Nice catch. Okay, so let's look at this quantum info problem. So this is the same problem as before, except that I just replaced the integral by this formal moment variable. So this is the objective function, and then so here you really see that there are 2 types of constraints, right? There are the constraints on the variables themselves, so that there must be binary. So a square equal b square equal 1. But there are also constraints on the moments. So it means that you also have polynomials describing the moment constraints. So this, this factorization constraints here. So you have two semi-algebraic sets, one for the variables and one for the moments. And you can do as usual and define moment matrices and quadratic modules. I will do a bit of insights on that.
So the only thing that relates to your x variables and mu is the support.
Exactly.
Otherwise, there are different.
There are different graphs. So this is the usual hierarchy, but a bit modified. So your set X lies in the support of the measure big X, and also the measure belongs to a semi-algebraic set that defines the nonlinear moment constraints. So here it's exactly the same notation for the moment matrices, but they are a bit more complicated. And also here the quadratic module is a bit more complicated. So it depends on the polynomials that describe the support, right, the nonlinear moment constraints. And this is one example of moment matrix. So here you index the moments by a basis of your polynomial, right? Of your polynomial space. So at order 1 already, you have 1, x1, and x2, right? But then you also need to consider the formal moments of degree 1. So this m10, remember, when you evaluate it, it's the integral of x1 with respect to your measure. And same for m01. So you have 4 variables, and then you have 4 indices. But it's very different from an optimization problem in 4 variables, because there are connections between this moment variable here and this one. So let's forget about this left lower part. So here the two blue variables are actually have to be the same, because if you integrate x1, then it's the same as integrating the integral of x1. And same here for the 2 red variables and for the green variables. And actually, you can simplify a lot this moment matrices, but still the size grows quite. Okay, so it's quite late, but the message that you can have in mind is that, okay, I can build a moment matrix with these non-linearities. I just need to add more rows and more columns for every basis element of this complicated polynomial ring. And also the quadratic module is also more complicated. So you need to consider sums of squares of polynomials, but also the sums of squares of moments. So you have more possible terms. And so what we could prove, and what's funny is that the proof is almost the same as for classical polynomial optimization. So if you look into this paper by Putinar and by Schmütgen, the proof is almost the same. And so every positive moments polynomial has a sum of squares decomposition. And as an immediate consequence, you get convergence of this NPA hierarchy or this classical Lasserre hierarchy. But let us just see what the actual bounds are. So for the first problem, the covariance problem, so we run the hierarchy at order 2. So we get an SDP with 4,000 variables, so it's quite easy to solve. And then we found an upper bound of 4.5. But then that's great news. That's great news because the physicists found a lower bound of 4.5. That's very good teamwork. For the second problem, it was not a good teamwork because the bound they have, so they conjectured that the maximum was 3 for this ugly bilocality problem. And actually, it's very hard to solve this problem because here you have a degree 6 constraint. So you need to start at order 3. So you already have an SDP with like 30,000 variables. but this is still doable. And actually, we found a bound of 4. And we could, this extraction algorithm that depends on the rank of the moment matrix. So we were extremely lucky and we could apply it. And then we found a measure so that basically solves this optimization problem. And that implies that the bound is actually 4, not 3. So that's how the story ended for the classical case. For the quantum variant of this problem, we were not able to solve it. So let me conclude. So I talked about all these sparsity exploiting hierarchies. And I also mentioned that this is implemented in Toolbox. So feel free to try it and to contact us if there are bugs, if you can't install it. One thing to remember is that if the problem has a lot of structure, then you can solve possibly huge problems with the sparsity exploiting techniques. And I also presented some extensions to nonlinear moment problems. So far, we only considered these classical variants of quantum Bell scenario, but there might be a lot of other applications. And something I didn't mention is that on the theoretical side, we also obtained some results stating that if the moment polynomial is positive, then it might not be a sum of squares, but you can always perturb it a little bit to obtain a sum of squares. So we could generalize this nice result by itself. So it looks like maybe useless theoretical results, but actually it's quite interesting to study that because this is actually what your numerical solver does, right? It adds some floating point error perturbation of your input polynomial. So it's interesting to see what happens when you use your favorite numerical solver. So the further topics that remain unexplored, so there is the topic of conditioning. So already in the dense case, almost nothing is known about the conditioning, except that it seems bad in practice. For term sparsity, there was no algorithm to do the extraction, but I think now Jonas can tell you how to do that. And so I was also thinking about possible applications of these moment polynomials, and in particular, there is this class of nonlinear optimal transports called the Gromov-Wasserstein, on which such techniques could be applied. And this is the last marketing slide. So why should you do polynomial optimization if you don't already? And why should you study these nonlinear moment problems? Well, this moment SOS hierarchy is very powerful to model these problems, and is very efficient when you have a lot of structure. So that's good to try it. And thank you for listening. Yes.
So the result by Resnick that you showed basically says that you could do this sum of squares decomposition in the coordinate ring of the toric variety corresponding to the.
Wait. I'm gonna try to switch back directly to it. Oh yeah, it works. Yes.
Right. So in the Motzkin example, for instance, we would have a quadratic. So we'd have a degree 2 element in the coordinate ring of a toric surface.
Maybe
decompose it as a sum of squares of linear things. Are there like more complicated? Could you imagine like other rational varieties in which this works?
Absolutely not.
It's impossible, or you haven't thought about it?
I haven't thought about it. Yes, Marcus.
These problems which stem from a physicist, actually the variables themselves were not appearing, only these moment variables were appearing, right?
Exactly.
I mean, for the support, for defining the support,
exactly so.
Variables were appearing, but in the goal function they were not appearing.
Exactly, there are no moment polynomials, non-pure, that appear here. Exactly. So we couldn't find also applications where you really need general moment polynomials. And this
maybe you need them because of the support.
Yeah. You need to have them, and you need to index your moment matrix by them, but they don't appear explicitly.
I mean, how do you explain that the physicists, by experimenting, found that 3 is a lower bound for the maximum, and you found 4 is the true maximum? It seems very unlikely that they find 3 by experiments, or was it just that they guessed some?
Oh, they just did a lot of samplings. I think they used some kind of linear programming relaxations that were not strong enough to.
Or maybe it's because it's plus minus 1 constraints that. Maybe because. So I was wondering why they find an integer, but maybe it's just because it's plus minus 1 constraint.
Maybe.
There's some local maximum 3.
Yeah, but why is it 3? Why?
I don't know. I also don't know what's the meaning of the second part.
Because there is 1/3 in the object. Okay.
Maybe.
Thanks.
It's a Newton polytope.
Yes.
The objective function. So is there something which is similar when you have constraints? Can you?
This is what term sparsity does.
Know about the sum of square multipliers? What's the support of it?
That's what term sparsity does. It generalizes the notion of Newton polytope also to the multipliers. That's how I see it.
Yeah, but it's not.
And Newton polytope is also Newton polytope only works with the monomial basis. But when you're in the symmetry adapted context, and it's also some generalization. Newton polytope for symmetry adapted.
It's more general.
Intuitions that local maxima are not so intrinsic.
The support of the constraints might the zeros.
But they do. So they do. So in the general algorithm, you really check if the product appears either in the support of the objective function or the support of the constraints. It's really constraint dependent.
You have the two alpha.
Of course, you need to take the squares. You are looking for an SOS decomposition, so you need to keep all the possible squares. And if you take the Newton polytope, then some of these squares are removed. Or if you take another basis, then the squares are different.